First of all, I would like to thank you for giving me a chance to talk about my research associated with NERSC. This is a great opportunity. It's an honor. My title, the talk title is Solving the Multiscale Multiphysics Puzzles in Tokamak Edge. And actually, this project started on NERSC a long time ago, NERSC computers, and still thriving on NERSC computers. Allow me to present a few wordy slides because I really would like to explain how my research journey has been shaped by 50 years of NERSC. I became a NERSC user in the CTRCC and MFECC era. Many of you may not remember this, but the CTRCC was Controlled Thermonuclear Research Computer Center between 1974 and 76. And at that time, in 75, I became a graduate student using CDC 7600, a small computer. But as you can see on the right-hand side, CDC 7600, we were using black and white monitor, and we used this to program it. And our storage was a card. This is the card punching machine, and this was our storage. And I don't know how this happens. And sometime later, we were using, a telephone modem. It makes a funny noise. And I built my first major code on NFCC computer in mid-80s, actually. So I was a transport code guy. However, until the launch of G-Seaborg in 1999, that's a whopping 512 core machine. Until then, I was still mostly an analytic theorist. When G-Seaborg was installed in 99, my concept of physics research changed in a transformative way. I felt what was coming in the computing world. And I was frustrated at that time about the limit of analytic theory. Fusion is actually by nature governed by nonlinear multiscale multiphysics. There was no way really to make good progress using a paper and pen. And I really cracked out of that concept of paper and pen. And Tokamak boundary was one of the most severe examples in governed by nonlinear multiscale multiphysics. I saw a way. So I recruited a few graduate students. At that time, many people called me crazy. And then we started building a multiphysics kinetic code XCC for Tokamak boundary physics. At that time, still is true, mostly. They were trying to save computing time by taking perturbative approach, assuming scale separation between background dynamics and turbulence dynamics. And so that way they were solving only like 1% turbulent part of the whole plasma. If I want to solve the whole thing together, multi-scale interaction between turbulence and background to turbulence, I needed about 100 times more computing power. Then I envisioned that the computing power would grow explosively according to Moore's law, and I got lucky. I was right on one thing here. And then with the launch of Seaborg 1 and 2, my dream was becoming more realistic. We rapidly completed the first multiscale physics code, which was parallelized. And that we called it XCC0, the first one, using particle in cell technology. As you can see on the right-hand side, this was a research news, and that was a big news in among people like me. That was 2001. And this code accurately follows 3D plasma particle trajectories. Thus, the evolution of the background plasma was simulated together with the Monte Carlo neutral particle trajectories, or already multi-physics neutral particle physics, and the background particle trajectories, all the distorted trajectories due to inhomogeneity in Tokamak. And we had to use simplified electrostatic potential solver in realistic Tokamak geometry because the computer on the Seaborg was not that powerful yet. So we had to assume the electrostatic potential is constant along the field line due to high electrical conductivity. And then at that time, this was a coincidence, or I got lucky. There was a PhysEx subcommittee heavily emphasizing the necessity for a multiscale, multi-physics code to study the Tokamak edge physics problem. And they were emphasizing it for a few years, but all the proposals before me just failed because such code did not exist. And XCC was at that time the only such a code. And it's thanks to NERSC. Naturally, when I wrote the proposal, I was awarded with just consecutively Proto-FSP, SciDec2, SciDec3, and SciDec4 centers. And we recruited a dream team and applied math, computer science, and performance engineering. We developed XCC into a modern parallel code using patchy solver now. We didn't have to have a simplified solver. And we were getting tremendous help ever since from NERSC programs, especially NISA programs. And then XCC became one of the largest Insight Award codes since 2007, all thanks to NERSC. 2009 became Oscar Joule milestone code on Jaguar. And early science code, they called it CARD, or the subsequent new computers at OLCF. In 2012, XCC became a GPU code on Titan, one of the earliest GPU code actually. In 2016, it became one of the ECP application and co-design codes in WDM app and COPA project. They became one of the most successful exascale codes on Frontier, and the Aurora code actually, which is we are testing on smaller scale. And XCC has now developed into being for SciDec5s. And I'm no longer a PI now. All the other project, I was PI or co-PI. Now, I would like to get into physics and how explain to you what kind of important multiscale physics we have been attacking thanks to NERSC system, NERSC programs. There was a long time ago, there was a baseline H-mode mystery, and we solved it on Seaborg. Tokamak plasma spontaneously bifurcates into H-mode. We call it high confinement mode. On the left-hand side, we can see that this is the edge of, we call it magnetic separatrix. On the right-hand side, you can see magnetic separatrix. Inside is the confined plasma. Outside is the unconfined plasma. Magnetic field lines actually touch the wall. And the issue was the importance of this H mode was that fusion requires certain pressure, temperature, and density in the core to have a economical fusion reaction. However, the slope is determined by plasma turbulence, it's self-organization. And when you extend it to the wall is here. If the size of the machine is small, that means economical. The wall material will melt. There's no wall material which can withstand such a high pressure and temperature. There was a big issue in Tokamak program. However, in about 1980, was accidentally found that as we heat the plasma more and more, the plasma just makes a transition into H mode where there's a steep pedestal. As you can see now, we don't have to have the wall very far. The plasma temperature and density goes down tremendously, and this is relatively safe. And this is the important problem. And they didn't know how did it happened. And they found out by experiment that there is an electric field forming right in this layer. And you can see there's a negative electric field. And that somehow had a, relationship with this spontaneous transition or bifurcation into this high mode. And XCC, we attacked this problem, and we found out that in Tokamak, what happens is that there's something called gravity drift, and we normally have a gravity drift, particles drift downward. So when the particles follow field lines and down, 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 and then there's a magnetic mirror effect, and so particles have to mirror, and then the particle ions again go down, down. Because of the X point, they can never come back. Without X point, it will just come back, again, just come back and forth again. Other particles, other classes of particles are there. They drift down, 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 and then because of X point, they just got lost from the plasma. What happens is that ions get lost. That means that now the plasma is negatively charged at the edge, which means electric field is negative. And that has to confine the ions now, this field. And that was we call it electrostatic confinement. That was the source. So actually, I myself discovered this ion X-point orbit loss on Seaborg. And this is one of the big theoretical discoveries in magnetic fusion at that time. We published multiple papers, and not only us, but other people also took the idea. There are a lot of papers on this. And then there was another mystery. Tokamak plasma rotation is very important. They find out experimentally. And if there's a strong rotation in the core plasma, the confinement gets better and plasma stability gets better, turbulence gets better, everything gets better. However, when they found out the plasma was the rotation of the plasma was going up, there was a mystery. There has to be conservation of momentum. Where is the momentum coming if a plasma is accelerating? And so we attacked this problem. There was some theories that plasma turbulence is making the plasma rotate, but turbulence does not have much momentum. Waves don't have much momentum. So we did the simulation. We actually discovered that the momentum source is from the edge core interaction. It's plasma is unconfined here. They actually interact with the outside world. And whatever rotation is here in the unconfined area, there's an interaction. This interaction is actually from what I just described, X-point orbit loss. So consider plasma rotating, this particle rotating this way, and they get lost, which means that we are losing the momentum here by this particle. And then we find out that there's a loss cone, and the loss cone is not empty. It's continuously refurbished by plasma turbulence and Coulomb collisions. So this is the black line is where loss cone is outside here. And this is actually turbulence effect. And we find out that if we calculate the torque from this loss, and then angular momentum change, then they are equal and opposite sign. So we have proven that the momentum is actually coming from the outside. Whatever rotation we can give, bigger rotation we can give at the outside, we'll have a bigger rotation in the core. And MIT actually found this out experimentally. Okay, this movie is playing first. I stop the movie and explain this. And there was another, big question. This LH transition I just talked about, LH bifurcation. How is it happening? Uh, there was no really real first principles explanation or understanding. There were only simplified models, and the modelers actually argue against each other. This is I'm right, yeah, I'm right. And we decided to attack this problem. And this problem was actually too small for, uh, too large for then smaller NERSC computers. But fortunately, we had a lot of inside award. Uh, so we used the Titan to study this. And we actually got this is a theta direction, poloidal direction. And this is a minor radial direction. We just unfold it and then study something in the box here. So this is what's happening with turbulence. And watch this carefully, please. So let me start from the beginning. And the black line is separatrix. You can see that turbulence is now getting suppressed. They are disappearing, and then the disappearance of turbulence is propagating inward. You can also see plasma flow that way and then plasma flow the other way. And this is what we call, this is a shear flow, actually shearing away turbulence. And we found out that this shearing was initiated by nonlinear Rayleigh stress, and that transfers turbulence energy to shear the flow, and that starts the turbulence suppression. And this actually shows what happens with the shear from the code. When the flow is sheared one way and the other way, you can see they are stretched, and then this turbulence is beginning to disappear, sheared away. This was another important achievement, and published papers on this. And all of these became SC highlights, actually. There was another big issue, actually, pretty big issue. Plasma, say, ITER has 100 megawatts of exhaust energy coming out. Any reactor will have exhaust energy. We did not want exhaust energy to go everywhere and damage the wall. So we wanted to have only a certain part to be hit by this exhaust heat. So at the maintenance time, yearly or whatever, maintenance time, we just change the material here. It's called the diverter plates. You can see at the bottom, this is the ITER design. However, the issue was that when we studied all the machines, existing machines, this lambda Q is actually the measurement of width, heat channel width along this toroidal direction. And since the shape of all the plates here are different, we map it to the midplane, outside midplane here, and we measured it. This width was getting smaller and smaller as the magnetic field was becoming larger and larger. And ITER is actually here. When we go here, it's only 0.5 millimeter, according to this current data. And with this, ITER was actually getting doomed by some scientists. 100 megawatt hitting just, such a narrow band here, it's gonna burn the tungsten diverter here. There's no material which can withstand. The width, design width was around 6-7 millimeters actually. So we attacked this problem to see if that happens. We first see the simulation, and then these are the empty shapes. We open shapes. We actually rediscovered all the experimental scaling, which is about 1 over BP, all the way to CMOD here. And all of a sudden, when you apply the same code to ITER, it jumped to 6 millimeters. And why was the problem we studied? Why is there something wrong with the code or the same code? And we found out that ITER, with such a high, not only high magnetic field, but also very, very large machine. ITER edge was in a different physics regime from the current machine. And there was a lot of electron directional turbulence, edge turbulence in ITER. And that turbulence was spreading heat load on the diverter plates. That's what we found out. And this was a big news. And ITER and the community was demanding us to validate it on the current machines. ITER, however, was already accepting this view, and they were using turbulence actually. And I have this was electrostatic turbulence. I have an arrow which I'll explain a little later, another new discovery. So speaking of validation, we really tried to validate it. Oh, one more thing before. Using all these data, we put in all the data and all the simulation data into the new physics regime, and I put it into a supervised AI program, all the experimental data and simulation data and the possible physics supervised the formula, combinations of formula. We found a few different formula. The program was spitting out of different formula, and this formula was fitting all the data right, all the simulation data right. So I call this simulation anchored machine learning, and this was published in 2021. Now this turbulence spreading, broadening of the lambda Q, validation on the current device was quite important. And this was done in D3D very recently. And Darren Ernst published it in a Physical Review letter just a couple of weeks ago. So what they saw was that there were two types of plasma. One was called wide pastel QH. The other type was called QH. I don't need to explain this actually. And in the wide pastel QH mode, that was black here, delta N over N, that's turbulence strength. And this is the radius, and this is the separatrix, plasma separatrix. And they saw that when the plasma transits into the QH mode, another different mode, the lambda Q, that's the diverter heat load width, kind of jumped, became about twice. And they saw that. And then they actually measured the turbulence. They saw that the ion turbulence level was not increasing, but electron turbulence level was really increasing a lot. It jumped. And this was predicted by XCC, and they confirmed it. And then we used the Perlmutter. Perlmutter is not now large enough to do these simulations. And the star was the XCC result, square was the experimental result. So we agreed, lambda Q agreed, and we also found out, also in this case, electron directional turbulence was the one responsible. So this is a good example. Machine learning is only an interpolation. Just following machine learning and being pessimistic is not a good way. Extrapolation to future physics regime is not in the machine learning regime. We need to have a first principles prediction using HPC. And that is something I would like to emphasize. So I call this simulation anchored machine learning. And the surrogate model I just told you, a simple surrogate model, will become more accurate as more studies are performed on leadership class computers. Another discovery made recently, first made on Perlmutter. Being on NERSC program, we were doing some early science studies. And as a separated surface, as I said, inside this surface, it's confined. However, I already said that ion orbits there is a loss orbit. What about electrons? And we all assumed in all the theories and experiments that this surface is good. We found out with electromagnetic simulation, this surface is no good. This is this 3D simulation done on Perlmutter. This is the breaking of a last confinement surface. That's a separatrix surface. This was shocking. This phenomenon was known by actually a long time ago, but that was all static case. And in Tokamak, this was induced by external coils or MHD. However, we found out this is an intrinsic property by turbulence in a tokamak plasma. And Poincaré found it a long time ago. He got King's award for finding homoclinic tangles. And another thing I would like to emphasize in relation to the data management slide I'm going to show, this is extremely thin. These lobes are really thin when we're talking about turbulence. And this is, I want to emphasize here, this is a subgrid scale. Our grid cannot capture this. Since this is a particle code, we can actually follow the particles and map out the magnetic field line like this. And the diverter heat load with figure I showed you, electrostatic to electromagnetic case, EM, the heat load width was becoming wider due to this effect. And I have ideas of how to utilize this phenomenon to further broaden the diverter heat load width. And for the fun of it, let me take just 30 seconds to explain what homoclinic tangle is. The magnetic field lines actually go around the torus. This is just cross section. Go around. When it goes around, let me use this. It comes to the next point here, and then it comes to the next point here. X point in Tokamak is actually hyperbolic fixed point. Magnetic field lines can never go to X point. The distance becomes shorter and shorter. So when it comes back here, the field lines perturbation will become longer and longer due to preservation of magnetic flux. Magnetic flux has to be preserved. Divergence to be equal to 0, all those things. Okay, so as it approaches the X point, which is the hyperbolic fixed point, this lobe becomes longer and longer. Turbulence also can travel the other way. That the same thing happens, and then now you can see the tangle lines, and electrons follow basically these field lines, and there is connection between inside and outside. That's a diverter area. Plasma is now connected. There is transport of electrons between inside and outside. This is a really new findings we have in a steady state tokamak, where even if we assume when we control the disruption and then all the instabilities, this will exist. Another discovery, let me check the time here. I'll try to finish it quickly then. On Pearl matter, there was another important study just done, which became, as usual, the invited talks at APS and IAEA. Plasma fueling is quite important for ITER and the nuclear reactors. We need to control the fueling to keep the pedestal high, and then the fueling sound. So we need to know how the fueling is done. Recently, experimentalists found out from actually radiation, the Lyman alpha radiation, that plasma fueling is coming from inside, even though all the neutral particle recycling is mostly from outside. Fueling is outside, but the fueling actually is from inside. How did that happen? So we did a simulation, and the orange line is actually the XCC result with Degas-2. That's the Monte Carlo neutral particle code with atomic physics. It's coupled to XCC as a library, and we qualitatively reproduced this result. This was another big success, becoming a big news now. Okay, so I want to emphasize, since the time is up, I'm not going to explain this. We actually, using NERSC, thanks to NERSC, we actually developed a baseline capability for federated data system using Corey, and we used the K-star data and to stream data and analyze streaming data in situ actually. And we used the Adios Dataman, and ESNet was really big part of that in this project. Federated data system needs streaming data reduction, first starting at data source and then streaming analysis and reduction on remote HPC. So we have this technology and using only 6 Core nodes. When K-star people at the site took 12 hours to analyze multi-scale data. It took only 10 minutes. So we have that this technology probably can be used on HPDF. I'll skip this one. Okay, so let me go to conclusion and discussions. I would like to emphasize that my career path has been steered and shaped by 50 years of NERSC. I actually was using NERSC for 49 years. The kinetic code started on G. Seaborg, and Seaborg has been riding the rapid rise of NERSC computing power. I was very lucky. I had the right betting actually. And XCC became one of the most successful exascale codes and multiple SIDEC5 codes. 3 most dangerous events in ITER and future Tokamak fusion reactors are plasma disruption, as you know pretty well. This is mostly cold physics. And the other 2, collapse of edge pedestal by edge localized mode instability. I didn't explain it, but by using our code, we can actually study how the profiles evolve into instability. And then the melting with diverter surface material, which I emphasized in this talk. These 2 are edge physics. We have made substantial first principles-based understanding and improvement of the 2 edge issues. They all became SC highlights, and they are subject to nonlinear, non-local, multiscale self-organization of multiphysics. Not an easy subject. We need HPC. XCC will continuously study the 2 edge physics problems to help commercialization of a fusion reactor. And on NERSC computer, we'll keep on using basic physics research and validation on present-day tokamaks. The Perlmutter and future Tokamak, future machines will be pretty big size to actually we can study a lot of physics. On exascale computers, we'll be studying large scale predictive study for ITER or fusion pilot plants. And XCC actually could become an HPC exascale digital twin. And also, as I have shown you as an example, produce predictive surrogate models. Thank you very much. I can't hear you.
Oh, I'm talking to myself. So thank you. Thank you very much. And thank you for all the kind words about NERSC. And thank you for the explanation of the physics. I really appreciate it. I found it really interesting. As you said, we are a little bit over, but if anybody wants to ask a quick question, you can type it into chat or Q&A, and I'd be happy to take it. If not, I want to thank you again, and thank you for being a NERSC user for, what you said, 49 years. That's amazing. And I look forward to our interactions in the future as well.
Thank you very much.
Okay, thanks everybody.